Hello, everyone. My name is Ivan, and I'm a graduate student at Georgia Tech. Today, I would like to present to you our study on predicting mobility flows in urban areas in the context of road network resilience optimization. Precisely, the goal of our study is to predict daily mobility flows between census tracts in an urban area. Now, data on urban mobility flows can inform many important applications, such as understanding transportation connectedness, studying socioeconomic activities, predicting disease spread, and can also inform urban resilience planning decisions. And yet these data are rather difficult to collect because good data would often require extensive use of sensors or surveys. So in our work, we investigate whether flow prediction models can be fitted using available data from certain urban areas and then generalized to other areas where travel flow data are not available. And this is done at a relatively high spatial resolution, namely in our case at the census tract level. And in addition to prediction accuracy, we aim to evaluate these mobility flow models in the context of a downstream decision-making process. In particular, we know that floods can compromise the integrity of road networks and create a huge impact on our daily socioeconomic activities. So that's why we aim to evaluate how prediction errors in the mobility flow models can affect mitigation planning process against floods. Mobility flow models. So we will first look at the study areas in this study, which are 3 metro areas around Washington, D.C., Seattle, and Chicago. Here we are seeing some statistics about the areas. And here we can see some color maps of the number of outgoing trips from each census tract. Now this will be the ground truth mobility flow data we will use for training our models. In terms of models, we have these so-called mobility flow models which estimate the number of trips from an origin zone to a destination zone. Now these two zones need to be different. We can look at the traditional models first. Now these models are usually, they usually have a formula form. They make some very simplifying assumptions. And they only involve a few number of features. On the other hand, we have machine learning models which allow for a richer set of features and could be useful in our case when we try to predict mobility flows on a higher resolution spatial parcellation. So the traditional models include what's known as the gravity model, which has been widely studied. Its name comes from its resemblance of the gravity law in physics. So it basically says the probability of a trip happening is proportional to the populations of the area and of the origin and the destination zones. And it also decays with either the power law of the distance or an exponential form of the distance. Another class of traditional models are some models that use what's called intervening opportunities, which is a feature we will introduce shortly. Next, let's move on to the machine learning models. First, we have the random forest, which is one of the best performing models in a recent study, which aimed at predicting nationwide highway mobility flows. And the other one we have here is what we call the extended gravity model. So some past works have already considered adding a few additional features to the gravity model. So instead of just having the population of the zones, you would have maybe one or two more features multiplied to that product. But in our case, we expand that to include any number of features. And please don't be daunted by this formula. It simply says that the number of trips between from zone I to zone J is estimated with the product of the power law of a set of features, and then of course multiplied by some function of distance. In our case, we use what's called Poisson regression. It is a technique that has been shown to have better performance to fit gravity model than some other techniques such as linear regression. The feature data we use include population, jobs, and income data from Census Bureau, and land cover data from United States Geographical Survey, and road network data from OpenStreetMap. So here we are looking at a summary table of all the features associated with either the origin zone or the destination zone. There's kind of a symmetry here. So you would have one set of these features for the origin and also for the destination. This includes population data, area and land cover data, and then some job data. Now these are another set of features. These features are associated with not just one zone, but the pair of origin and destination zones. So of course this would include distance, which can be either Euclidean distance from between the centroids of two zones, or the road distance, which is the shortest distance one needs to travel along the road network to get from one centroid to the other centroid. Now, the intervening features, as we have just mentioned earlier, is defined as the sum of a particular feature value of all the zones that are closer to the origin than the destination. So this is also something that's, that people who study mobility or migration or trade would be familiar with. So to take an example here, if we say the bubble sizes represent population of each of these zones, then the intervening population from this zone here to this zone would be the sum of the population of these states whose centroids lie within this circle. So note that we are using centroids here, so this is actually considering Euclidean distance. Last, we have our ground truth data, which is the mobility flow data. Now, the traditional model in their original form cannot be fitted to data from multiple areas. However, machine learning models can. So what we did was we fit the machine learning models with the data from two of the study areas. And then we use the model to predict mobility flows for the third area. And that gives us a threefold cross-validation. We use the cross-validation to test how well the model predictions can generalize from available data to other metro areas where the mobility flow data are not available. And these are the metrics we use for accuracy. This includes common part of commuters, or CPC, which is a commonly used feature for this kind of mobility prediction. And we also have CPC-D, which is a variant to CPC, and then some other features that we are more familiar with. The results table can be found here. And as expected, the machine learning models provide much more accurate predictions than the traditional models. Among the machine learning models, we see that random forest has the most accurate predictions, while the extended gravity model with exponential decay function for distance produces slightly less accurate predictions. But also we want to highlight that the extended gravity model requires much less time and memory than random forest. And here we can see a spatial distribution of prediction errors for gravity model, extended gravity model, and random forest. And this can also be found in the paper. And let's move on to measuring the decision error, which is we want to evaluate how the errors in the prediction of mobility flows can influence downstream decision-making process. Precisely, we want to evaluate how well can mobility predictions inform optimizing road upgrades to maximize human mobility during floods. So to do this, for scalability reason, we extract 4 counties from the 3 study areas to apply this method here. And before we go into the method, we first need to look at the data we use. So first, of course, we need to know the flood zones. This data are from FEMA. And again, we use road network from OpenStreetMap. And of course, we still need the ground truth mobility flows data. The process looks like this. First, we take the road network and the flood map to compute the intersection between these. So the red segments are all the parts of road segments that are what we call blocked by these flood zones. So if the segment is blocked, then we assume all the trips passing through the segment would be infeasible. So we combine this affected road graph with mobility data, and then we would get how many trips are infeasible on each road. Then we can optimize based on this data here to choose the best set of road segments to fortify under a given budget constraint. And then this will give us a fortification plan. So to be more precise, we first evenly distribute either the ground truth mobility flows or the predicted mobility flows to all the possible paths between tracked pairs. So we assume from zone I to zone J, if there are 100 trips, then those trips are evenly distributed across all the paths between zone I and zone J. Now, as we take the intersection of the flood zones and the road network, we know that how many trips are infeasible on each of the affected road segment. So now we can greedily fortify the flooded parts of road segments to maximize restored infeasible trips. And here we assume that the budget needed to fortify a road segment is proportional to the length of that road segment's intersection with any flood zone. And in the end, we combine the ground truth mobility flow data and the fortification plan generated by either ground truth data or predicted data to evaluate the number of infeasible trips. And the results, we can see that the first color map here represents when the optimization algorithm is given the ground truth mobility flow data. And this would be the number of restored infeasible trips given a certain level of budget. The other ones here are the decision errors. So when we apply, when we feed predicted data instead of the ground truth data to the optimization algorithm, it produces different results than if we did feed it with ground truth data. And this is comparing how that fortification plan performs versus the one that's given ground truth knowledge. So we can see that for the 3 machine learning models here, the errors are relatively small. But for the less accurate gravity models predictions, the optimization results in much fewer trips restored in many of the zones. So we can see how that error actually propagates to this process, while for the other models, it didn't. Here we have a more comprehensive view on the results across many different budget levels. So we can see that this 0.2 level was the one we just saw on the previous slide. So the gravity model had a poor performance, but the other ones are actually really close, although the accuracy of those machine learning models in terms of CPC are not even over 0.7. And we can also see that this trend continues as the budget increase. So the takeaway here is really that decision process could inform choice of flow model. For example, we can consider the result of this particular mitigation planning with the greedy algorithm, either given the predictions of random forest or extended gravity model. We can see that they are pretty close. And we know that although extended gravity model produce less accurate data than random forest, the extended gravity model actually requires much less time to train and also much less memory than random forest. So in this scenario, a decision maker might be motivated to favor extended gravity model over random forest model. And that is how the particular downstream decision process could inform the choice of flow prediction model. And that is all. Thank you very much.